So for position time graphs, you're going to be given a graph that has position on the y-axis and time on the x-axis. And this is page 7, by the way. And so I'm just going to jump in and start doing the problems. Um, so example 1 says, part A says, describe the object's motion in words. And so what this graph is showing us is the position of some object over time. So it's showing us the motion. And so if you imagine a number line, let's say 0 is here, and every notch is going to be 1 meter apart. So that's 1, 2, 3, 4, 5. Let's go to 8 right there. So from 0 to 3 seconds, we look at 0 and 3 seconds, and we look at the positions at those times. Here's position at 0 seconds, and here's the position at 3 seconds. So at the start of the clock, the object is at position 3. I'm going to draw a little person here. And as time goes on, for the next 3 seconds, the person will move to 4 and then eventually to 5. So the person will end at 5. So what did the person do? They just moved to the right. So for this, we'll just say moved forward or moved to the right. We switch sometimes. Sometimes we say right, sometimes we say forward. Okay, so from 3 to 4 seconds, we go to the graph, and we're going now from these two positions here. They're moving from position 5 to position 8. So if I go over here, they're going from 5 to 8. And so again, they're moving to the right. But there's something else we can get from this. So they are moving forward or to the right. But not only that, if we look at the graph, we can compare how fast the person is moving. So here's the slope at the beginning, but the one we're looking at right now is 3 to 4 seconds. We can see that the slope is more steep from 3 to 4 seconds. So this is faster. Oops. And this would be slower relative to each other. So we can also just say they're moving faster. Can be a little qualitative about it. Okay, next one is 4 to 7 seconds. So this right here. The person is staying at position 8. And they're staying there for 3 seconds. So we would just say that the person is motionless. And in physics, we like the word rest. That means the same thing. So if you are motionless, you are at rest, is what we would say. Okay. Next one is from 7 to 8 seconds. So from here to here. And the person is going from a position of 8 to a position of 2. So now they're going here, starting here, and going there. So they are moving backward. Or you can say left. It all has to do with the shapes of the slopes on the graph. So um, on this graph, when the slope is positive, and in math class they tell you that this is positive, then it's moving forward. If it's like this, such as this one, it is moving backward. And if it has zero slope, or just a flat line, then it is at rest. So like here. All right. Cool. This question, what is the position at 4 seconds? Well, this graph has position, so if we look at 4 seconds, go up to the line, that's going to be a position of 8. So we just say 8 we have to put units. These positions, remember we said they were spaced out a meter apart. These over here. So um, position 8 meters. Okay. I'll just leave that there in case we need it later. Okay. Next one says, what is the displacement? There's an equation for this. Delta x equals x2 minus x1. This is the displacement. Is this. So we also call that delta x, but means displacement. And so all we do is we look at the times. We don't want times in this equation, we want positions. So at 3 seconds and at 7 seconds. So I'm looking here, and then I'm looking here. This is a position of 8, and this is a position of 5. Okay, so this is T1 and this is T2. This would be X2 and this would be X1. And so now we know our X1 and X2. So it's going to be 8 minus 5. We'll keep showing our work. We'll substitute, go step by step. And I need to move over here to have some space. 8 minus 5 will give you 3 meters of displacement. Okay, let's talk about the meaning of displacement. What we just showed is that the person starts at 8 and they move to 5. Displacement is how far you had to move from where you started to where you ended. So they started here and they moved 1, 2, 3 meters to the left. Let's keep going. Oh, I'm sorry. Made a mistake there. They moved to the right. So how silly of me. Um, we got a positive number. Sorry. So we're showing that the person moved from a position of 5, and later on they were at a position of 8. It's been a long day. All right. The next one is average velocity. We have an equation for this, which we used on day 1. T2 minus T1. This one turns out to be very easy because they already give us the times. This is T1 and this is T2. So we're going to put those on the bottom, as you see there. So that's going to be 4 minus 0. And now, just like we did in the previous problem here, where we found x2 minus x1, that's what we're doing. We're doing the exact same thing here. So I'm going to look at 4 seconds, which has a position of 8. So 4 is a position of 8. Subtract. At time 0, it is a position of 3. Of course, you can type this in your calculator. I recommend typing in the whole fraction. Just say 8 minus 3 over 4 minus 0. I don't have one in front of me, so I'm just going to calculate this. This comes out to 5 over 4, which is 1.25 meters per second. Okay. Okay, the last one. What is the instantaneous velocity? What we do here is we figure out the slope. And what I really mean is, what is the rise over run? Let me make this brighter. What is the rise over run? So I'm going to go back to the graph. Before we answer that question exactly, let me just erase all this. just remembering the concept of slope. Um, Here we have four sections of the graph, this one, this one, this one, and then this one. And each of those has a slope. And here's how we do rise over run. We always go from one point to another point. And so let me use another color to illustrate this. So for the first section, I want to go from here to here. From the left point, we always start from the left and we go to the right point. Okay, so we can't just go straight like this. The way we get rise over run is we go up or down. In this case, we're going to go up. So we go up 1 unit, and then 2 units. So sometimes I'll show it like this, where I go up 1 and 2. And then we go over 1, 2, and 3. And so if V is equal to rise over run, we would show the work by saying V is equal to going up +2 and going over to the right +3, and your calculator will give you 0.6666, and we can just round that off to 0.67 for this one. So that is the instantaneous velocity for that section. If I try the same thing for this section here, we would go from this dot to this dot, up 1, 2, and 3, and over 1. So I'm just going to show the fraction, that's 3 over 1, which is 3 meters per second for that little section there. Let me change colors. If I want to go from this point to this point, we see that all we have to do is do a run, 1, 2, 3, and there is no rise. It does not go up or down. So that's 0 rise over 3, which of course 0 over 3 is just 0. So V equals 0. That is a 0 slope. And so the last section, we're going to go from this point to this point. Sorry, we always start from the left one and we go to the right one. This time we're going down because you wouldn't go up. There's nowhere to go from there. So we're going to go down 1, 2, 3, 4, 5, 6, which is down, so that's a -6. And on the run is 1. So the fraction then would be -6 over 1, which your calculator will confirm that it is -6 meters per second for the velocity. So I kind of skipped showing my work, but for each of these we would have wanted to write rise over run, and we should have said V equals this amount and then finishing off there. Okay, so that's how we do slope, but let's go back and answer the question at 1 second, they say. So we've already done it. If we go to 1 second, the rise over run for this segment that 1 second is on, that's all we care about now. Well, we calculated that first, it's this one. So what we would want to write down there is exactly what we put here. So that's the kind of work we want to show for this last one. And that would be the answer.